Good morning, everyone. Today's topic of this lecture is your single phase semiconductor. So, in previous lectures, we have already discussed about many type of semiconductor components, many different type of semiconductor devices, and the application and what are the benefits of these semiconductor devices nowadays. So already we have seen that in our day-to-day life and industries and many field we are using semiconductor or power electronic devices. So it has a wide range application, and now it is necessary to understand or study about these power electronic devices because it is very useful. And power electronics means that we are controlling the power, which is your electrical term, by your electronic or semiconductor devices. So these two words make electrical plus electronics, that you are controlling your electrical power by using electronic devices. So this is your power electronics. Now let's come to the next point, that what is single phase? Single phase means that you are using only one phase and one neutral wire. Okay. And in terms of electrical, there are single phase and three phase, two phase. So in this lecture, we will study about single phase semi converters. Semi converter means that it is not fully converted. Okay, the output is not fully converted, it is semi converted. That's why this is called your semi converter. And what is converter? Converter means that it may be convert your AC to DC or DC to AC, or what you required actually. If you want rectification, then you have to use rectifiers which convert from alternating current to your DC current. Now if you want that AC to AC output, so you required AC to AC converter. If you want your fixed DC to variable DC, then in that case you required your choppers. So these are the different kind of converters. Now we will focus on semi converters. So converters basically use semi conductor devices or semiconductor components. It may be our thyristor, BJT, diode, or GTO, IGBT. So as a switch, you can take any components of power electronics. Now let's discuss about the course objective of this semi converter devices. So course objective of this lecture is that to introduce the student about basics of your power semiconductor devices, and the different type of converters. And after this lecture, I'm expecting from the student that student will be able to understand what is your semiconductor devices, and what are their applications, and what are and waveforms which you are using in semi converter devices. So in this lecture, we will study about semi-converter devices. Now, what is converter? So converter may be your rectifier circuit, and uh, it is divided into two parts. One is your uncontrolled rectifier circuit, another one is your controlled rectifier circuit. So uncontrolled rectifier circuit, what do you mean by uncontrolled rectifier? Uncontrolled, it doesn't mean that it would be totally uncontrolled and you are giving some input and you are not getting output, or you are getting any kind of output. But uncontrolled means that you are using uh, diode, which is also a semiconductor device, but you can't control its output voltage, right? Because a diode has two terminal. Okay, it has two terminal and two layer device. So once it is in forward biasing, and once its voltage become higher than its uh, initial voltage. For silicon it is your zero point 0.7 electron volt. So it starts conducting, and holes and electrons will start flowing through your p and n junction, and electron will move from n layer to p layer, and holes will move from p layer to n layer. So the conduction will start. But as you voltage apply across these terminal, and your anode is positive and cathode is negative, it is becoming in forward biasing. In this case, it will conduct and the current will start to flow. But you can't control or control the output voltage by delaying some angle, or by applying some gate pulse. So that's why this is called your uncontrolled rectifier circuit. Right. Now let's come to the next point, that what is your controlled rectifier circuit. So controlled rectifier circuit, that still you are using semiconductor components or semiconductor devices, but you have to use some controlled semiconductor component. So it may be your SCR, it may be your IGBT, it may be your GTU. Depends upon that what kind of control you require. So, why SCR is called your controlling semiconductor device? Because it has three terminal. One is your anode, another one is your cathode, and third one is your gate terminal. So it has four layers and three terminals. When your anode terminal is positive with respect to your cathode terminal, so SCR will be in your forward biasing, because there are three junctions, J1, J2, J3. So J1 and J3 will be in your forward biasing, and J2 will be in your reverse biasing. So for the conduction of current, what you have to do, that you have to make the junction J2 from reverse bias to forward biasing. So to make it forward biasing, you have to apply some gate pulse. And now it will depend upon you whether and when you want to apply gate current across the SCR. Okay, when you apply only voltage across the anode and cathode terminal of SCR, then what is happening, that uh, that the anode will be in positive, anode terminal will be positive and cathode terminal will be negative, but there is no gate pulse, so SCR will not be in conduction mode. As you apply gate pulse at the terminal of your uh, SCR, gate terminal of SCR, then what is happening, that by applying gate pulse, you are injecting some electrons at the junction J2. So there are excess number of electrons, and due to n number of electrons, electron will start to move from uh, uh, cathode to anode, or towards your p layer. So movement of hole and electrons will start, and the current will start to flow. So this is the basic difference between uncontrolled rectifier circuit and controlled rectifier circuit. So by using this SCR and GTO, IGBT, you can easily control your output voltage. Now let's discuss about what is semiconductor. So basically, semiconductor is called your single coordinate converter. Single coordinate converter means that in this case, the voltage and current will be in positive direction, That's why it is a single quadrant converter, and it has only one polarity of output voltage and current. Uh, for example, because there are four quadrants. On x-axis, if you are taking voltage, and y-axis you are taking current. So right hand side of that graph, the voltage will be positive in right hand direction, and in upward direction current will be positive. So that is your first quadrant, okay, or single quadrant. So the polarity of your voltage and current will be one polarity. It may be if it is positive, then it will be positive. So it has only one polarity of output voltage and current. That's why this is your single coordinate converter. Now, why this is called semi converter? Because in single phase conversion, we are using two SCRs and two diodes, and both are connected in the bridge configuration, and that's why this is called your semi converter, because two SCR meaning that you are using two controlled semiconductor components, and two diodes that is also your semiconductor components, but it is your uncontrolled semiconductor device. So in semi converter we always use two SCRs and two diodes for its bridge configuration. So it can be arranged in two ways. One is your symmetrical and another one is your asymmetrical. So what is your symmetrical? Let's discuss that. First is your half bridge converter. So this is your single phase semi converter, in which you can see that we are using two thyristor T1 and T4, and another one is your two diodes, that is your D2 and D3. There is a single phase, and this is your load. So let's talk about your case first, in which you are using inductive load. Inductive load means that there is a inductance. So load is your highly inductive. Okay. Now, when you apply voltage over here, this is your AC voltage. When you apply your AC voltage, what is happening? That for your positive half cycle, this terminal will be positive, and this terminal also will be positive, and this terminal will negative, and this is also negative. If this terminal is positive and this terminal is positive, now you can see that if this terminal is positive with respect to this, so T1 will be in your forward conduction mode, and if this terminal is negative and this is your positive, then diode that this thyristor will not be conduct, okay, and it will be in your reverse blocking state. Now, uh, now you want to from forward blocking state to, you want that the T1 must be in your forward conduction mode. So what you have to do, that you have to apply some gate pulse through this gate terminal to SCR or thyristor T1. Okay. So when for the positive half cycle, T1 will be in your forward blocking state and T4 will be in your reverse blocking state. So it would be easy that you can apply gate pulse over here. So T1 will be in your forward blocking state to forward conduction state. Now for positive half cycle, you can see that there is two diode. This terminal is your negative. So you can see that if this terminal is negative, then diode D3 will be in reverse biasing, because this anode terminal is negative with respect to cathode. So diode will be in your reverse biasing, and the current will not flow through this uh, uh, in this circuit, and this is your diode D2, which is in your forward biasing because cathode is negative with respect to your anode. So you can see that for positive half cycle, the suitable components is your T1 and D2. Okay, so you can apply gate pulse at gate terminal of thyristor T1 and diode is automatically in your forward biasing. So what we are doing at angle alpha. Alpha is your delay angle. Alpha may be your 30 degree, 60 degree or 90 degree or 45 degree, which kind of output voltage you require. So the value of alpha will depends upon this output voltage. Okay, so let's assume that we are triggering our thyristor at an angle alpha. So T1 is triggered and it starts conducting. Okay, so T1 is triggered and it starts conducting. And when it conducts and diode is already in your forward biasing, so the circuit will completing through this loop. Okay, the current will start to flow from T1 load D2 and this is your supply. So through this loop, the current will start to flow. Now, so single phase half controlled bridge due to positive half cycle, you can see that T1 and D2 is conducting. Triggering angle may be your alpha to pi and T1 and D2 will be in conduction mode and T4 and D3 are in reverse biasing mode. Okay. Let's talk about your negative half cycle. So from this diagram, you can see when you apply negative waveform over here, so what is happening? This terminal will be negative and this terminal will be positive. When this terminal is negative, it is making thyristor T1 in reverse blocking state and uh, this terminal is negative, then T4 is in your forward blocking mode. So by applying gate pulse, you have to uh, turn on the SCR and that by applying gate terminal, gate pulse, the thyristor will become in your forward conduction mode. And if this terminal is your positive, then D3 will be in your forward biasing and D2 will be in your reverse biasing. So D3 in your forward biasing and D2 will be in your reverse biasing. So T4 and D3 will be conducting for more second. Okay. And T1 and D2 is in your reverse biasing. So you can see that due to negative half cycle, D3 and T4 are conducting and D2 and T1 are in reverse biasing mode. Okay, so the loop for this mode will be the current will start to flow through this mode. You can check that. Okay, like this. Okay. The current will start to flow like this. So this is your half bridge converter and you can say this is your semi converter in which you are using two SCR and two diode. Now let's talk about your load, which is your R load, in which inductor is not in is not connected in the load. So in this case, you are using two SCRs T1 and T2, two diodes T1 and D2. So what is the difference between these two diagrams that if you want to compare that, here we are connecting two SCR in series, okay, and two diode are also connecting in series with each other. But in this conduction mode, that in one parallel line, that one SCR and one diode is connected, and one means that two SCR is connected in parallel to each other. So you can also take this structure also, T1, T2. This is your AC supply and this is your D1, D2. So this is your single phase semi converter with RL load, in which one SCR and one diode is in series. Okay. And here is another SCR and one diode is in also series. So T1 and D2 in a same lane, and T2 and D1 is connected in a same branch. So you can see that for positive half cycle, again, this terminal is positive, this terminal is also positive, this terminal is negative, and this terminal is negative. So you can see that for positive half cycle, okay, when you apply positive gate signal, then T1 will be in your forward blocking mode, and your D1 will be in your forward biasing. So suitable thyristor and diode for this positive half cycle is T1 and D1. Okay. So when you apply positive half cycle, T1 and D1 will T1 and D1 is conducting. When T1 and D1 is conducting, then what is happening? That the loop will be followed is your T1 RL load, D1 and supply voltage. So the current will flow through these terminals or this loop T1 RL, D1 and your supply voltage. Now you can see from the diagram that when you apply single phase, this is your input voltage. At this voltage T1 and D1 is conducting, and now it's depend whether when you want to turn on this SCR by applying gate pulse. Here we are taking alpha delay angle, which is less than your 90 degree. It may be your 30 degree, 60 or 45. So this is your angle alpha. For positive half cycle at an angle alpha, when you turn on the SCR, then thyristor will start to conduct. T1 and D1 is conducting, and the output voltage you are getting, is from alpha to pi. Okay. You are not getting output voltage from 0 to pi. You are getting your output voltage from alpha to pi. Okay. So this is your positive half cycle, where alpha is your delay angle. Let's talk about your next let's talk about your next uh, terminal, next waveform. Suppose for negative half cycle, which is from pi to 2 pi. For negative half cycle, you can see that when you apply negative voltage over here, then this terminal will be negative and this terminal will be positive. this terminal will be negative and this terminal will be positive. So T2 is in your forward blocking state and D2 is in your forward biasing because this terminal is negative for your second half wave, which is a negative loop, negative waveform. So T2 and D2 is suitable for this conduction mode. Now we will apply gate pulse at the terminal of thyristor T2. So what is happening? T2 and D2 is conducting, and this is your delay angle alpha. So instead of pi, the SCR will start to conduct at this point, which is your pi plus alpha. So you are getting output voltage from pi plus alpha to 2 pi. Again for positive half cycle, you are getting your output voltage. So you can see from this waveform that for positive and negative both cycles you are getting only positive half cycle. Okay, you are getting positive half cycle in both the cases where T1 D1 is conducting from 0 to pi and pi to 2 pi. T2 and D2 will be conducting. When thyristor is not conducting, then the voltage drop across the SCR will be this VT1, which is equal to your Vm sin alpha. When thyristor conduct from alpha to pi, okay, alpha to pi plus alpha, there is no voltage drop across the SCR. Okay. Now, when this SCR is T2 and D2 is conducting, then the voltage drop across the SCR will be minus Vm. Okay. And for this period, this is your Vm sin alpha. Again, if T1 is conducting, that there will be no voltage drop across thyristor T1. But when T1 is not conducting, that there is a voltage waveform across this SCR VT1. So this is your semiconductor rectifier, uh, which is a semi converter, where we are using two SCR and two diode with your RL load. Now let's start with another circuit in which the components are same, two SCR and two diode we are using in this circuit. One additional diode which we are using, that is your freewheeling diode, and the load is your RLE, resistance inductor, and this is your battery. So let's start with the positive half cycle. Positive half cycle, this thyristor T1 and D1 will conduct. Okay, so the current will start to flow like this. Freewheeling diode will not be in your conduction mode. So diode at an angle alpha, you are triggering the SCR. Okay, so you are getting the output voltage VAB, and thyristor is conducting pi plus alpha. But you can see that the SCR T1 is conducting only for um, alpha to pi. The SCR is conducting only for alpha to pi, and for pi to alpha, freewheeling diode will conduct. Why is it happening? When you apply positive half cycle, T1 and D1 is conducting, and the current path will be from T1 to load and D1 and so on. When you disconnect the supply or negative voltage appearing T1 and D1, because of inductor and this battery, what is happening? The energy which was stored at the time of your positive half cycle by this inductor, it will start to release this energy, And this battery will behave like a source. When it will behave like a source, then the voltage at this terminal will be higher than this terminal. Okay? The voltage across this terminal will be higher than this terminal. So freewheeling diode will be in your conduction mode and it will be in your forward biasing mode. So freewheeling diode will start to conduct, and you can see that from 0 to pi, if you talk about your positive half cycle, if you talk about your positive half cycle, and you are triggering thyristor T1 at an angle alpha, then the thyristor will start to conduct from alpha to pi. For this particular period, you can say for this particular period, when your waveform is negative and thyristor T2 is not turned on, okay, and D2 is not in your, forward conduction mode. Because of inductor and battery, freewheeling diode will be in your conduction mode, and the current path will be like this. Okay, so the current will flow through the freewheeling diode. Now, the voltage across thyristor T1 will be 0 because at this particular time, thyristor T1 is conducting, and when T2 is conducting, the voltage drop across thyristor T1 will be minus Vm. When VT2 is conducting, the voltage drop across this SCR will be 0 because freewheeling diode is in conduction mode. At this particular point, T1 is conducting, and that's why the voltage across this SCR is your 0. The load current, if you talk about the load current, when T1 and D1 is conducting, the load is increasing. Load current is increasing because the inductor is charging. When T1 and D1 turned off, still current is flowing through the freewheeling diode because, and it is decreasing gradually just because of inductor, because at this mode the inductor will oppose the change of current, and the energy which was stored at the time of this particular positive cycle, the energy will release through the inductor and the current will start decaying. At this point, you again turn on thyristor T2, and at this particular point, this is 2 pi because the waveform is going in positive direction. So thyristor T2 will be in your reverse blocking mode. At this point, T2 and D2 is conducting. At this point, again your freewheeling diode will be in your conduction mode, and the energy which was stored during this particular waveform, it will be released by the inductor. So the current direction will remain same because this is the property of inductor, that it always oppose the current flow of sudden current change in any circuit. So you can see that you are getting continuous current in RLE mode. So this is your semiconductor device. Now let's come to the output equation, which is very important. So the output equation we can get by this formula from the diagram, that this is your sine waveform. It is conducting from alpha to pi. So the output voltage you are getting from alpha to pi. So 1 by pi integration from alpha to pi Vm sine omega t dot d omega t. When you integrate this sine omega t, and after solving this equation, you will get the output voltage which is equal to Vm upon pi 1 plus cos alpha. So this is a very simple formula, and Many numericals is asked in your exam, which is depend upon this formula. So this formula must be learned, and this is very simple. You can easily learn this output voltage formula of semi converter. So output voltage of semi converter is equal to Vm upon pi into 1 plus cos alpha. Now, if you want to derive the equation for RMS value of output voltage, what you have to do? Of the voltage, okay, where Vm is your maximum value of the voltage, and by integrating this equation, you can easily get the RMS value of your output voltage. So Vm V square m upon 2 pi omega t minus sine 2 omega t upon 2. If you integrate this equation, and how can you integrate this equation? That you know the formula of cos 2 theta is equal to 1 minus 2 sine square omega t. When you put sine square omega t is equal to uh, 1 minus cos 2 theta upon 2, after putting this equation, you will easily get, you can easily integrate this equation. So after integration, you will get omega t minus sine 2 omega t upon 2. Okay, limits from alpha to pi. So v square m upon pi divided by 2. Now you can put a limit from in this equation. So at omega t, you can put pi minus alpha minus sine to omega t upon 2. You can put uh, pi pi minus sine 2 pi upon 2 minus sine 2 alpha upon 2. So you know the value of sine 2 pi is always 0. So you are getting, and this equation v square m can be converted in your in terms of your uh, supply voltage. So this can be written as your v square s upon pi, and this is your pi minus alpha plus sine 2 alpha upon 2. So this is your RMS value, square of your RMS value. When you want to find out only RMS value, then you have to take the root of this equation. So you will get RMS output voltage of semi converter is equal to Vs pi minus alpha upon pi plus sine 2 alpha upon 2. So this is all about your semi converter, in which you are using two SCR and two diodes. And we have seen the different mode of operation for R load, RL load, and RLE load. And we have also we have also done the mathematical analysis, and we have find out the average output voltage of this semi converter and RMS output voltage of the semi converter, which is very important. And some numericals are asked in exam, which is depend upon these equations. So you must learn these equations, which is very important. Now let's come to the MCQs, which is very basics and which is depends upon this lecture. So let's talk about this MCQs. So first is your in a single phase fully controlled converter, the the diode of an uncontrolled converter are replaced by SCR. As you know that diode is your uncontrolled device, and SCR is your controlled semiconductor device. So in single phase fully controlled converter, the SCR or diode of an uncontrolled converter can be replaced by your SCR. Now let's talk about your next question, that in a fully controlled converter, The load voltage is controlled by in a fully controlled converter. The load voltage is controlled by controlling the firing angle of the converter, because you know that if you want your controlling output, you are using SCR. By the changing of your alpha angle, you can easily control the output voltage of your converter. A single phase half wave controlled converter always operates in the a single phase half wave controlled converter always operates in the discontinuous conduction mode, because there is no freewheeling diode or SCR by which they can conduct the current. The voltage form factor of a single phase fully controlled half wave converter with a resistive inductive load is uh, compared to the same converter with a resistive load. The load current form factor of a single fully controlled half wave converter a resistive inductive load is poorer compared to the same converter with a resistive load. Now, which of the given device is the fastest switching device? So, MOSFET is your fastest switching device. Next question is, in the forward blocking mode of a silicon controlled rectifier, the SCR is in on state, in neutral state, forward biasing state, in off state. So it will remain in your in off state, because to turning on the SCR you have to apply some gate pulse, then it will come from forward blocking state to forward conduction state. So it will remain in the off state until and unless you apply gate pulse at the gate terminal of the SCR. Now, the anode current passing through a conducting silicon controlled rectifier is 20 ampere. If its gate current is made half, what will be the anode current? If you are making it half, then the you know anode current will remain same. It will also 20 amperes, because anode current will depend on upon your load. Now, a silicon controlled rectifier is turned off mode when its turn off time is greater than the circuit turn off time, less than the circuit turn off time, equal to the circuit turn off time, and none of these. So the silicon controlled rectifier circuit turn off time must be less than the circuit turn off time, because before getting the circuit turned off, it must be turned off. So the device will be turned off before getting the circuit turned off. So the silicon control rectifier turn off mode, turn off time will be less than the circuit turn on time. Thank you. So this is all about your semi converters. And now I want to summarize this lecture, that why it is called your semi converter, because you are using two thyristor and two SCRs. Okay, and you are getting positive pulse over here. You are converting the voltage. For RLE load, you are getting your continuous current conduction, because it is not the value of current is not zero in this mode. That's why this is called your continuous conduction mode. So if you talk about your RL load, you can easily draw the waveform for this load, and you will get this waveform. Okay, so what is the difference between RL and RLE load? That you are adding extra component, which is your freewheeling diode, and freewheeling diode will conduct when your uh, supply voltage is cut, and the current will flow through your freewheeling diode and load. Okay. So this is your R and RL load, and this is all about your semi converter. Now you can see that in this mode the current is also positive and voltage is also positive. So that's why this is called your single cordon converter, because it has only one polarity of output voltage and